Sun is a star. Stars are hot gas. They have very complicated structures, but they are usually multi-layered. In this case, we are looking at different layers of the sun. This is not the right scale, just a cartoon showing different layers. We start with the core at the center. Core is the hottest part of the sun. Then next layer is radiation zone. In radiation zone, we have transfer of energy as a wave. That's the main reason this is called radiation. The energy is produced at the core, then we have transition of this energy as a wave. In the next layer, we have convection zone. Convection zone means energy transfers as a convection current. So this is very similar to boiling water. What you see in the boiling water, you see hot layer moves upward, cools down, and moves downward again. And we see this convection currents or convection cycles. Next layer is photosphere. Photosphere is the visible part of the sun. Above photosphere, we have chromosphere. Above chromosphere, we have corona. First important thing about these layers is that density decreases when we move away from the core. So in this picture, core is the highest density or compactness. It's super compact, and corona is the lowest density. So for density, moving away from the core, density falls down, density decreases. What about temperature? Temperature is a little more complicated because we expect to see temperature declines if we move away from the core, but this is not the case. So we start from the core. Core is the hottest layer. It's around 10 million Kelvin. Moving to the next layer, we have a huge decrease in temperature. It's around 2 million Kelvin. So we start from 10 million. Next layer, radiation zone is 2 million Kelvin. Moving to the next layer, we have much lower temperature, which is around 6,000 Kelvin. And it's almost the same for photosphere and convection zone. So this layer is around 6,000 Kelvin, 5,800 Kelvin. Moving to chromosphere, we have a temperature between 2,000 to 4,000 Kelvin. So far, so good. So what you see from the core to chromosphere is you see temperature decreases. But then suddenly for corona, we have a jump. Corona is 1 million Kelvin, round about 1 million Kelvin. So corona is hotter than chromosphere, photosphere, and convection zone. It's not as hot as radiation zone. It's not as hot as the core, but it's still extremely hot compared to chromosphere. So you have around 2,000 to 4,000 Kelvin, and suddenly we have a jump to million Kelvin. And it looks strange, but in order to explain this jump in temperature, we need to understand the magnetic structure. Okay, so corona is hotter than chromosphere, photosphere, and convection zone, but we don't expect this high temperature. In order to explain this high temperature, we need to add magnetic fields to this picture. So far, we have seen materials and different layers of the sun. But if we have an environment with a lot of charged particles moving around, we also have very complicated magnetic field. So these magnetic fields are fields of force. So they can be smaller, they can be larger, they can have different sizes, different shapes. But generally what they do, they add force. So let's say we have a proton in this layer, And because there is this magnetic field, if this magnetic field is strong enough, they can carry these electrons or protons or other charged particles along their lines. So let's say this particle is a proton from a hot layer. So in this case, it's close to radiation zone with a few million Kelvin temperature. Then we have this magnetic field. This particle will move along this magnetic field because there is a force. But remember, this particle has very high energy and temperature. Then this particle moves to another layer which is cooler. So what happens, we have a temperature difference, hot particle in a cool environment. So this particle will release this energy. This happens to other particles along other magnetic fields. That will explain why corona is much hotter, because these particles, they can carry energy to corona and make it much hotter than other layers in the way. Another important thing about this magnetic field is that because particles move along its magnetic field and they lose energy, these areas are cooler. Okay? So because they are cooler, they look darker than their neighbor points. And these are called sunspots. When we look at the sun, basically what we see is photosphere. And sometimes we see dark points on photosphere. These dark points are cooler regions of the sun. And the reason these areas are cooler, because particles carrying energy, they are losing this energy. So this part is losing energy, it's cooler. This part is losing energy, it's cooler. And these are called sunspots. So in summary, core is the hottest layer. It produces energy and it has the highest density, or it's extremely compact. Photosphere is the visible part of the sun. Anytime you look at the sun, what you see is actually photosphere. We have sunspots. Sunspots are darker, cooler regions of the sun because particles move away, they carry energy away, and they look darker. And we have granules. Granules are these smaller points. For convection zone, again, these points are losing energy. Okay, so these points are coming above higher temperature, they lose energy, lower temperature, then they move down. So you will see these kind of granular structure. You will see granular structures in this layer. For chromosphere, we have plagias, we have filaments, and we have prominences. These are little flares. For corona, we have high temperature. Be careful, this is not the hottest layer. The hottest layer is the core. Second hottest layer is the radiation zone. Third hottest layer is corona. We have X-ray because it's extremely hot. We can have X-ray from corona, but we don't have X-ray from chromosphere or photosphere. We can have coronal lobes. Coronal lobes are particles that are moving along this magnetic field. So you will see something like this. These are called coronal lobes. We have streamers and we have coronal mass ejection. Coronal mass ejection are particles that can escape. They have enough energy. And these are all associated with magnetic field. So if we have strong magnetic fields and these particles don't have enough energy to escape, we will have loops. If we have weaker magnetic fields or these particles have enough energy, they can escape. So it will be coronal mass ejection. And these coronal mass ejections, they can produce a lot of problems. They can damage structures if they move towards the Earth. They can produce a lot of damage if they move towards Earth or our infrastructures. There is a question about rotation period of the Sun. First important thing is, because this is a gas, not a solid object, different points rotate in different speed. Okay, so for rotation period, we are looking for a sunspot close to equator. Okay, so for example, in this case, 1 and 2 are not good examples. They will give you a different number. They will give you rotation period for this location or this location, which is different. Okay, so the best option is to find the sunspot close to equator, which is 3 in this case. Okay, and the next step is follow different pictures and find another picture with 3 at the center or close to the other edge. Okay, and the main idea is we have this rotation. If we use this picture and compare this picture with this picture, the amount of time for this sunspot move from this point to this point is 1/4 of the rotation. Okay, so take this day and find the difference. In this case, it's around 6 days, which is a rough approximation. That's okay. So 6 days from this point to this point. Then this is 1/4 of rotation. I have to multiply by 4. So 6 times 4, rotation period with this sunspot is 24 days. Sometimes you can't find another image with this sunspot at the center. You find another image with this sunspot close to the other edge. Again, find the difference, which is 13 days in this case. But for this case, one edge to another edge is half rotation. You have the other side. So you have to multiply by 2. Find the difference, 13 days. Multiply by 2, 26 days. And you will get a different number because this is just a rough approximation. Either one is fine. Either go with one edge to the center or one edge to another edge. And you can be creative. You can go with center to another edge. Okay? Main idea is to find a sunspot close to the equator. There is another question about CME speed. The main idea for this question is we observe a CME event close to the sun at a specific date and time. Let's say this is July 20th, specific time. Let's say this is 9. Okay, and there is a distance, so it will take time for this CME to travel from the sun to Earth. Okay, let's say we receive this event sometime around July 22nd and our time is 12. It's just an approximate number. Okay, so for this event we have around 2 days and 3 hours. The real number in your question is different. This is just the easy number I'm using to explain. Okay, so you have 2 days and 3 hours for this CME. Okay, then you have to convert to how many hours? 2 days are 48 hours and you add a few more hours here. This is the time. Now you have the time and you have the distance. That number is given and you need to find the speed. So basically So basically you take that distance, which is in miles, so distance in miles divided by time in hours. Okay, just take that number from your question. Time is the time difference from this point to this point, 48, 50 hours in this case. Then divide this number, and that will give you the speed, which is mile per hour, and you don't need to convert anything.